Hello everyone, this is Miss Fairman. Since I'm not there today, I thought we would try out this method of me giving you guys a little video about the notes. You have the guided notes. You can add the information as you watch this video, just like you would in class. Here you can pause things if you need more time, and in fact there will be some time for you to pause and try out the work on your own. That being said, let's go ahead and get started. So we are moving on in Chapter 5 to Section 2, which is about properties of rational exponents and radicals. And I just realized there's a typo at the top. That should be an of. And it occurred to me that perhaps we actually haven't talked about exponent properties. So just as a review, if you have two things that are multiplied together that are the same base, a, we add their exponents. So here is an example. If you have a base raised to a power and then it's raised to another power, you multiply their exponents. And here's an example. If you have a quotient, if you have a fraction where you have the same base and exponents, you subtract them. Here is an example where the numerator is bigger than the denominator. You would just get x to the third. If the denominator is bigger than the numerator, when you subtract, you get a negative number, or you can leave all those leftovers in the denominator as 1 over x cubed. If you have a negative exponent, recall that negative exponents just mean reciprocal. So we would write 1 over a to the m in the denominator. Or if the negative was in the denominator, we would move it up to the top and just get a to the m. So here are some examples. Then if we have a quotient raised to a power, we distribute the exponent into every part. If you have a product raised to a power, you distribute the exponent to every part. And if you have a to the 0, you get 1. So if you want, you could take a second and pause the video here. You could write all these down, or if you know them and you're ready to move on, go ahead and move on. So let's head to our notes packet and let's just do some examples. Since we know our exponent properties, it doesn't matter what the value of the exponent is, we can just do the properties that they say. So for example, in part A, I have two numbers that have the same base 7, and then they both have exponents. So what am I going to do when I'm multiplying those? I would add their exponents, 1/4 plus 1/2. The issue here is that I need a common denominator. So in order to add them, I can rewrite the second fraction as 2 to the 4th, and I end up getting 7 to the 3/4. In example B, this is an opportunity for me to raise a power to a power. This squared is going to be delivered to each product, in each part of the product inside the parentheses, and they already have exponents. So if I have 6 to the 1/2 squared, and then 4 to the 1/3 squared, I end up with 6 to the 2 over 2, or 6 to the 1 power, times 4 to the 2/3, because when I multiply a whole number 2 times 1/3, I get 2 over 3. Let's look at example C. Here again, I have a product inside the parentheses, and I have an exponent on the outside. So I can do a couple of things. I could rewrite this as a fraction because that exponent is negative, in which case I would have 1 over 4 to the 5th times 3 to the 5th, and all of that is raised to the 1/5 power. Or I could distribute first, so that negative goes to each number, so I would have 4 to the 5th to the negative 1/5 times 3 to the 5th to the negative 1/5. It doesn't matter which way you go, because either way you're going to end up getting 4 to the negative 1, and 3 to the negative 1, which eventually will be 1 over 4 to the 1 times 3, or 1 over 12. Looking at example D, we have a 5 over 5 to the 1/3, and then you can see it was already rewritten to remind you that if there isn't an exponent written down, there is always an invisible 1 exponent. So what do we do when we have a quotient? We subtract our exponents. 1 minus 1/3. You can find common denominators, or hopefully you just know that that would be 5 to the 2/3. Lastly, example E, we have 42 to the 1/3 and 6 to the 1/3, all of that raised to the second power. So here we're going to use our exponent properties backwards a little bit. So instead of having 42 to the 1/3 over 6 to the 1/3, I can rewrite that so that I have 42 to the 6th, but all of that is to the 1/3 power. And then all of that is being squared. And if I work from the inside out to simplify, it becomes a little bit easier, because 42 divided by 6 is 7. And then we'd have 7 to the 1/3 squared, which would just be 7 to the 2/3. So take a second, think back through those. Remember, you're using your exponent properties. And I know I'm blowing through them kind of fast, but I think that you know them from before. If not, again, take a pause, go back and look at them, make a note so that when I come back to class, you can go over them. All right, here is a good opportunity for you to pause the video and try the 4 problems at the bottom. Okay, welcome back. Hopefully you tried them. Here are the answers. Take a second, compare them against your answers. If you have any questions, go ahead and pause again and maybe ask your neighbor. All right, let's do some more examples. So let's go to example 2, using the properties of radicals. As a recall, remember that if you have a product, A times B, under the radical, you could split that into radical A times radical B. And if you have a quotient, A over B, under a radical, you could split that into radical A over radical B. These rules apply no matter what the index is. So if we look at example A, we can take the cube root of 12 times the cube root of 18 and make it the cube root of 12 times 18 all under the radical. If I do that math, I get 216, and maybe I happen to know off the top of my head that the cube root of 216 is in fact 6. For part B, here we have the 4th root of 80 over the 4th root of 5. Well, what if I just made it one big fraction, a 4th root of 80 over 5? That makes it easier for me, because if I simplify that fraction, I get the 4th root of 16, and 16 has a perfect 4th root. 2 times 2 times 2 times 2. So we get 2 as our simplified answer. For example 3, here we need to consider what makes a radical in simplest form. So here are some rules. 1, we have no perfect n root factors. So that means if it's a square root, we don't have any perfect squares. If it's a cube root, we don't have any perfect cubes. So none of those are left under the radical. Secondly, no radical fractions. So that means that we can't have a radical on a whole fraction, but it is okay to have a radical on part of the fraction. All right. And then specifically, the part that it's okay to have the radical on is the numerator. So this is the third step. No radicals in denominator. What that means is that we might have to multiply our fraction by something that would give us a whole value instead of a root. All right, so let's do these two examples. If I have the cube root of 135, in order to fully simplify it, and we've already done this, we need to find out if it has any perfect cube factors. It does. Because if we divide it by 5, we get 27, and hopefully by now you know that 27 is a perfect cube. This is 3 cubed. So that means we would have a 3 on the outside, and then cube root 5. For part B, we have the 5th root of 7. We can't do anything with that because 7's a prime number. And we have the 5th root of 8. So one way to think about this is, can we rewrite 8 as a smaller number with an exponent? And in fact, we can. So we have the 5th root of 7 over the 5th root of 2 cubed. Since we are looking for a 5th root, we need 2 more 2s. 2 more factors of 2 so that we'd have 5 factors of 2. So if we multiply by 1, written in the form of the 5th root of 2 squared over the 5th root of 2 squared, in the denominator, what we end up with is the 5th root of 2 to the 5th. And in the numerator, what we end up with is the 5th root of 7 times 4. So our numerator becomes the 5th root of 28, and our denominator becomes the 5th root, just becomes 2, because the 5th root of 2 to the 5th is just going to be 2. Great. So what happens if you have a denominator that contains more than one part? It's not just a simple root. Well, in this case, we have a binomial in our denominator. So we need to multiply by something that would make the radical cancel. If you remember from before, there's a thing called a conjugate. And remember, conjugates are things like a minus b and a plus b. So the a's and the b's are the same, but our signs in between them are different. When we FOIL those, we end up getting a squared minus b squared with no middle term. And not having a middle term is going to be important because we don't want to FOIL something and have root 3. If we just multiplied by root 3 in the top and the bottom of this fraction, we wouldn't get rid of the radical. So in this case, we've got 1 over 5 plus root 3. So if we multiply by the conjugate, which would be 5 minus root 3 over 5 minus root 3. In my numerator, I just distribute, so I get 5 minus root 3, because 1 times that is going to be the same. And in the denominator, this is now a dots. And for dots, it follows the multiplication pattern a squared minus b squared. So all we need to do is square this first term and get 25. And then square this second term and get 3 and subtract them. So our denominator is equal to 22. All right, couple more examples before you should pause and do a little practice. So if we are adding and subtracting like radicals, what that means is that in order to be a like radical, you have to have the same index and you have to have the same radicand. So that's the thing under the radical. So for part A, we do. We have an invisible 1 in front of the 4th root of 10. Plus 7 4th roots of 10. So 1 plus 7 means we're going to have 8 total 4th roots of 10. It's that easy. Same thing in part B. we have 2 times 8 times 8 to the 1/5, and we have 10 times 8 to the 1/5. If you think about it, we could GCF the 8 to the 1/5, and we'd have 2 plus 10, 8 to the 1/5. And we can go ahead and perform this math. So we just get 12 times 8 to the 1/5. For part C, in the past, we had to have the same index and the same radicand. We have the same index, but we don't have the same radicand. So what do I need to do? I need to simplify this first radical. If I recall, 54 is actually 27 times 2. That's convenient because 27 is a perfect cube. So 3 comes outside. Cube root of 2 is left over. Minus a cube root of 2. And remember, there was an invisible 1 in front of it. So our final simplified expression would be 2 cube root of 2. Okay, take a minute here and pause and see if you can answer these bottom questions. Okay, how did you do? Here are your solutions. If you got any of these wrong, I suggest that you pause the video and ask a neighbor for help, or rewind the video and look at the explanations again. And if those steps still don't help, go ahead and make a note on your notes so that when I am in class again, you can ask a question about the thing that you didn't get. All right, we're moving on. So let's do a few more examples. For example 6, we're going to simplify this expression. And we've done this with numbers, but now we've got variables. So remember, a cube root or an nth root, we're just looking for groups of n factors. So in this case, we're looking for groups of 3 factors. If I look at 64, luckily I already know that 64 is a perfect cube. So this could be rewritten as 4 cubed times y cubed times y cubed. Because if I use my exponent rules, then I know that if I added these two, I would get 6. So in this case, the 4 comes out because I can cube root it. One of these y's comes out because I can cube root it. And the second y comes out, which we then write as 4y squared. So that's our simplified answer. If we look at the fraction, remember, we can break our fraction into parts. So we can have the 4th root of x to the 4th in the numerator and the 4th root of y to the 8th in the denominator. And remember, y to the 8th is the same as y to the 4th times y to the 4th. So in my numerator, the 4th root of x to the 4th is just x. And the 4th root of y to the 4th times the 4th root of y to the 4th would be y squared in the denominator. Note, there is a little caveat here. Technically, the numerator should be written as the absolute value of x because we're not sure if it was a positive number multiplied 4 times or if it was a negative number multiplied 4 times. It's important that you know that that exists, but I'm not going to test you on that. All right, let's look at example 7. For example 7, we are going to simplify all of these things. So you don't have to do these steps exactly the way that I do them. I'm sort of explaining them widely or with all the parts. You certainly can skip ahead if you understand stuff. All right, let's look at this. So I'm going to rewrite this as all of things in groups of 4. So this is 16 is 2 to the 4th. I can have a to the 4th times a cubed because that would be a to the 7th. I can have b to the 4th times b to the 4th times b cubed because that would be b to the 11th. And then I have c to the 4th. So notice on the outside, I should have a 2. I should have an a. I should have one b, I should have a second b, and I should have a c. So the outside of my radical becomes 2a b squared, and then I have the fourth root, and the things that are left over underneath my radical are a cubed and c to the fourth. So that's the fully simplified answer for part A. All right, if we look at part B, we can use the same steps, or we can think about this. If I had just another y, I would be able to take the cube root. So this is x over the cube root of y cubed times y cubed times y squared. So if I had another y, another cube root of y, then I would be able to simplify the whole thing. So why don't I multiply it by 1 in the form of the cube root of y over a cube root of y. So now I have x cube root of y in the numerator, and in the denominator, this ended up being the cube root of y to the 9th, which would just be y cubed. Perhaps you are noticing that you don't have to write out the exponents like this. You can just look at how many times does 9 divided by 3, like what does that give you? It gives me a 3. Notice that would then be the exponent on my y for this problem. All right, for part C, when I have a fraction with a whole bunch of parts, I like to make sure that everything's all lined up. So I'm going to put my whole numbers over whole numbers. So I got 14 over 2, and then I like to leave a little space. So I got x just by itself, and then I had x to the 3/4 in the denominator. In the numerator, I have y to the 1/3. There are no y's in the denominator. And in the denominator, I have z to the -6th, and there are no z's in the numerator. So now I can take each part and simplify them. Well, 14 divided by 2 is 7. That would be in the numerator. X to the invisible 1 power minus the 3/4 gives me x to the 1/4 power in the numerator. There's nothing to do with y, so y's just stay as y to the 1/3. And while I could leave the z in the denominator, typically we like to have positive exponents. So the z to the 6th moves up to the top and becomes positive, because if I move it from the denominator up north, I did that by making it a -6, aka +6. So those are 3 examples of writing the variable in simplest form. All right, let's look at example 8. Here we're adding and subtracting. What do you need in order to add and subtract? You got to have like terms. So here I have a root y and a root y. They have the same index and the same radicand, so that makes them like terms. So this, easily enough, is now 5 root y. On part B, we got a lot of stuff going on here. They have the same index, so that means we're on the right track. And I want to simplify wherever I can. So here, if I have z to the 5th, I can actually simplify that because z to the 5th is the same as z cubed times z squared. So we're going to have a 12 on the outside, a z is going to join it, and then the leftover would be the cube root 2z squared. Z's and 2's are always frustrating. With this one, remember 27 times 2, and 27 is 3 cubed. So on the outside, we're going to have a 3 times the z that's already there, a cube root, the 2 left over from the 54, and the 2 and the z squared. So now I have like terms because I have cube root 2z squared, cube root 2z squared, and notice on the outside I have a 12z and a 3z. So it's important to note that everything has to be like terms. If this was not a 12z, then I couldn't do anything with it. I could GCF the root, but otherwise I couldn't do anything. But since they're like terms I can't actually subtract, and I end up getting 9z cube root 2z squared. That is my final solution. All right, go ahead and pause the video here and try these next few problems. Okay, how did you do? Same suggestions as last time. If you didn't get something right, I suggest you ask a neighbor and see where you made a mistake, or go back and watch the examples again, or ask Miss Fairman next time we have class. All right, that's all of the notes for you today. You can see your homework is here down at the bottom. You can grab one of the textbooks on the shelf if you want to, or you can review this video to make sure you understand it since we went through everything kind of fast. Thanks so much, and I'll see you guys next time.